In this video, we're going to look at the types of radiation. So the three main types that we've got are alpha, beta, plus and minus, and gamma. So in terms of what they all do, we'll talk about that in a bit more detail. But how do we know which one is going to occur? For alpha, this typically occurs when our Z is greater than 83. So remember, Z is our what? Atomic number. So for an atomic number greater than 83, we start to get alpha decay. For beta, plus and minus, they're a little bit different on which one's which. Beta plus is too many neutrons. Beta minus is too few neutrons. Or we could say too many protons. So in terms of that graph that we talked about, that stability radioactive graph, if we've got too many protons or too few neutrons for beta minus, we're below the line. So beta minus below the line. Too many neutrons is above that stability line. So we're at the top of the graph. And in gamma's case, we'll talk about that later. So let's look at alpha first. So alpha, we represent by the Greek letter A. Kind of looks like a squiggly fish. This is our alpha symbol. Alpha decay produces a helium nucleus. And a helium nucleus looks like an alpha particle. We represent it as alpha particle, and it's 2, 4. So it's just the nucleus. So what we mean is it's literally just helium, but it doesn't have any electrons. So it's just what's in the center, the nucleus aspect of it. So in terms of our notation, if we had some element, and we've got our Z, A, and this thing produces alpha radiation, then we would represent this by, it's not an equal sign, it's a goes to, just like a chemical reaction, goes to something, which is the new element, plus this alpha particle that's produced. So it produces a 2, 4 alpha particle, which is the helium nucleus. In terms of figuring out what the heck this thing is, it's just really a conservation. It's just like doing some maths. So if I had A on this side, and over here I've got 4, I can't have more or less than what I started with. So this then must just be A minus 4 to balance out. And then on the bottom, I've got 2 over here, so 2 have been taken. So this then becomes Z minus 2. An example of this would be if this was, say, 6, I've lost 4, this would now be 2 for a mass number. And then same thing here. I would just add up the numbers. So you can basically treat it like a math problem. You take the top line, and you take the bottom line, and they should equal to the starting point. So A minus 4 plus 4, the 4s will cancel out, I get back A. Z minus 2 plus 2 gives me back Z. So they have to be conserved. I can't just create or destroy anything. So that's alpha particles. We produce this alpha particle that's produced. It's a 2, 4, so you need to remember that. Or if you forget, remember it's a helium nucleus. So helium is atomic number 2, mass number 4. Just remember it has no electrons, which don't factor in here. Then you just chuck that in. So whatever it is goes to something plus that, and then work backwards along your lines to figure out what the original or what the produced product is. So that's your alpha particles. One of the important things to know with beta radiation in both plus and minus is it's producing an electron and a positron, which is basically an anti-electron. So we basically produce this electron, and in this case, electron has a negative charge, and it has no protons or neutrons. So we would represent it like this, and this is why they sometimes refer it to as the beta minus particle, because it's just the beta particle which happens to be an electron. The negative 1 implies a charge, and the 0 says that it has no protons or no neutrons. So this is your electron. On the other side, I can have a plus 1, 0, which is still an electron, so to speak, but it's a positively charged electron. So I would represent that as my beta plus particle. And this is what we call a positron. So this is our electron, plain old boring electron, and this is our positron, which is an antimatter particle to the electron. So positron and electron. In beta minus, I produce the negative charge, so I produce the electron. And in beta plus, I produce the positron. So let's start with beta minus. So this is the equation for it. So in beta minus, what is happening is that a neutron is decaying into a proton. And so it decays into a proton, produces an electron as well, and we get this thing here which is an antineutrino. So this becomes a subatomic particle. This part is not particularly important because really it doesn't do anything. It's a zero charge, zero proton, zero neutron particle, but it's what happens. So if you can remember it, it's excellent, but otherwise these are the priority things. This isn't going to change your answer if you're trying to predict something. It's just an important product. So beta minus, we get this neutron decaying into a proton. Remember when we talked about in the earlier section that you've got to balance the top and bottom lines. So when we look at that, we can see here that this line and this line all equal out. So if I start with a neutron and then it decays into a proton, so far the mass numbers are the same because it only had one and it only had one, but it was a one neutron and a one proton that have converted, and I've got 0, 0. So that's all good. On the bottom line, I had 0, I've gained 1, which is my charge, so I need to subtract a charge to balance that out. So in this case, it's conservation of charge. In this case, it was basically conservation of mass. But as long as the numbers balance out, you get what you wanted. Let's look at a better example of that. A general case would be if I have my element x, what's it going to decay into? It's going to decay into some other x, which we can work out, and it's going to produce these things. So we're going to get our electron, and we're going to get our antineutrino. So just for reference, this is the antineutrino. And when we talk about neutrinos in beta plus, it's just, again, it's the antiparticle of it. So if you remember that you put a line over it, it's kind of like saying no. So just like when you've got your old, like, we don't want any of this, they probably don't have these bits in them. That's your typical symbol for no. No smoking, no skateboarding, all the fun stuff. Not smoking, that is, that's bad. But, you know, every time you see a don't do this, they always give you this sign. And there's a line through it. So if you just remember, if we've got a line, then that tells us that it's a no, it's an antiparticle. If it doesn't have the line on it, then it just becomes the standard particle, it would be the neutrino. So this is what we've got. We've got element X, it's decayed into the new element X, it's produced this electron, and it's produced this antineutrino. So if we want to figure out what's the general formula for this thing to become, well, we look at the balance. We had Z, we've got -1, and we've got a 0. So in order to get a Z, this thing has to be +1 for them to cancel out. In the top, I've got an A, 0, 0, 0. This has to be A still. So this just becomes A. And remember that it becomes A because technically the neutron has become a proton, but the mass numbers are the same. This one has gained a charge, which offsets the negative charge, so the charges are balanced. And this is my general formula for the beta minus radiation. So the main points are beta minus is an electron. It produces an antineutrino, and you'll often see it as this slanted V looking thing. So that's my antineutrino. And we just balance the top line and the bottom line, and we figure out what our final product is, what's actually decayed from it. So that is beta minus radiation. In beta plus case, we've got the opposite effect. Remember in beta minus, the neutron decayed into the proton. In beta plus, the proton decayed into the neutron. So we're producing a neutron. As a result, because of the plus, we get our positron. So remember, this is the antiparticle to the electron. So this is our positron. And this thing is our neutrino. Doesn't have the line on it, so it's just the plain old neutrino. The subatomic particle, it's a 0, 0, has no effect on the equation, but it's what's produced. So positron is the main part. Beta plus produces positron, beta minus produces the electron. So if we've got our proton decaying into a neutron, we've got our positron, and we've got our neutrino, if again we check the lines, we go, all right, let's look across the top, and let's look across the bottom. We start with a +1, we've got a 0, +1, checks out. Along the top, we've got a 1, converted into a 1, which it went from proton to neutron, but we don't care. The mass is conserved. 0, 0, we're all good. So that's the general format, proton to neutron. Now let's look at a representation. If I have my X, ZA, and that decays into my new X, my unknown substance, it's going to produce my positron, and it's going to produce my neutrino. Now what I do is I just do exactly the same thing as I did with the beta minus and I did with the alpha. I look across the top and bottom lines. Here I've got an A, and A has to equal something plus 0 plus 0. This must be A. Along the bottom I've gained a plus 1, so this has to become a negative 1. They cancel out, and I get my Z again. So I've got whatever I had, subtract 1, they cancel, I get back to Z. This is the general formula for beta plus radiation. So often it's hard to tell, well, when does beta plus happen and when does beta minus happen? Beta plus occurs because we've got too many protons. So remember, beta minus was too many neutrons, and that's why the neutrons then convert themselves or decay into protons to try and balance itself out. In beta plus case, we've got too many protons. So the protons are saying, I'm going to take this upon myself, I'm going to convert back into a neutron and make myself more stable. So based off that, if you have an isotope that is excessively heavy in neutrons, those neutrons are likely going to decay into protons, and then you've got your beta minus. If you've got an isotope where you've lost a ton of neutrons or you've got a lot of protons, then those protons are going to try and decay back into neutrons to balance itself out and stabilize itself again, and then you've got beta plus. So that is the difference between plus and minus beta radiation. Now let's look at gamma radiation. So gamma radiation we denote by this Greek symbol, gamma, funnily enough. And in gamma radiation, what we're actually producing is a gamma particle, which is this symbol. Gamma particles are basically a 0, 0. They're just purely energy. So gamma is very high energy light, and where we talked about before, in alpha we produce a helium nucleus, which is a very heavy object. In beta radiation we're producing an electron, which is much, much, much lighter. And in gamma radiation, we're basically producing a massless object, which is just very high energy light. So if we were to look at a general equation before, where we have our ZA stuff, then it's just going to decay into something, but it's also going to produce gamma particles. And this just is how many. So this is your gamma particle, this is how many gamma particles. So it just produces n number of gamma particles. But you might notice, well, nothing's actually happened. So why would you produce gamma? Because at A, it's not making it more stable, and B, it doesn't seem to have done anything. You've still got the same thing. So we could theoretically just produce infinite gamma. This ties in with the E equals mc squared equation. Gamma is just energy. So we're releasing excess energy from a reaction. So typically what happens is that you'll have an alpha or a beta radiation occurring as well as the gamma. So an example of that might be something like you've got this, it decays into your new thing, it produces an electron. So what type of radiation is this? We're producing an electron, it's beta minus, and we also produce some number of gamma rays. So this part offsets, and we can work this out. This is our new element, so it is decaying, it's producing an electron in the beta minus radiation, so it is becoming more stable. And there's a difference in energy because the proton and the neutron are not the same mass. We can't have a change in mass, so this is released as energy in terms of gamma radiation. So it occurs as a result or with the other types of radiation. It's not necessarily just a standalone, emits gamma sporadically from that point. So in your book, there is a table that gives you a breakdown of all of those symbols. So the beta particle, the electron, the positron, the neutrino, antineutrino, n is just number of particles, gamma is the Greek letter gamma, and all of those pieces. So all of the things that you need to know for this topic. The other thing to consider is how dangerous are they, what is their penetrating power, and what is their ionizing ability. So in terms of the three, if we've got our alpha, beta, gamma, let's look at the three individually. So alpha we said is a helium nucleus. Beta was an electron or a positron. And gamma is just very high energy light. So now if we break that down, well, you could think about the mass of these even. If we were to say, think about the mass. Nucleus is very heavy. So this has got a lot more mass than an electron. So this would just be medium, and this has no mass. Because it's just high energy light, and light is massless. So medium, or we could say small, and heavy particle. In terms of the ionizing ability, it works the other way. Alpha is very ionizing. Beta is medium, and gamma is low. Doesn't have a lot of ionizing ability. Alpha, extremely ionizing. So this makes it very, very dangerous. However, when we look at penetrating power, which is a measure of how far it can actually penetrate through your skin, through solid objects, etc., alpha is very small. It is so big and so heavy that, and it doesn't have as much energy as the others, that it is stopped very, very easily. So generally alpha is stopped by like a piece of paper. Beta is a little bit more, on the vicinity of maybe a couple of centimeters or some really thick cardboard, and gamma is very high. Gamma can pass through most objects. It takes thick lead or solid concrete, things like that, to be able to stop gamma. So even though alpha is very ionizing, it seems like the most dangerous, but it's easily stopped. So most of it doesn't even get through your skin to actually cause any damage. Gamma, while low ionizing, has a very high penetrating power. So it can punch through the body quite easily, and that's where it can do all the damage. So this is a breakdown of your particles. Remember, alpha is our Greek letter. Beta, we've got R plus, beta minus. Zeros because they're electrons. And gamma is just our 0, 0 gamma particle. So that is our types of radiation.
Tell me pretty lies, look me in the face. Tell me that you love me, even if it's fake.